Alright, welcome back to I Love Chemistry Part 2. Oh, wait, no. Thank you. This is Arrhenius Problems Part 2. And we're going to now do C. We're going to determine the activation energy for this reaction, given temperature values and the rate constants. So you guessed it, I'm going to need my handy-dandy little calculator. And remember, when you get your calculator, you're going to want to do a couple things. I know for a fact that I have crap in my list, so I'm going to want to clear all of that out. So second quit. Second memory brings up all of my memory functions. I want to clear all lists, so that's 4 and hit enter. So now I have nothing in my list column, so I don't need any of that. Alright, I'm going to put this data in exactly as it appears in the table. I'm going to put for L1, which is typically your x-axis, I'm going to put the temperature values, and for L2, I'm going to put the K values. So really quickly, I'm going to pause you. If you would like, you can return the favor and pause me and do this yourself. Alright, so I've input my values. But I made a bit of a mistake. Look, I didn't even include that these were times 10 to the 9th. Oh, and I even put in the wrong value here for 12. Let me fix that. I have a confession. I didn't actually make a mistake and not include times 10 to the 12 times 10 because it's times 10 to the 9th because it would save me so much time if I simply batch transform this. So I'm going to go up and I'm going to say, oh dear Calci, who I so love, please change all of these times 10 to the 9th. So I want you to take list 2 and I want you to raise that times 10 to the 9th. And once I do that, Calci will say, I love you so much, Coach L, I will do that for you. And it does. You're the best, Calci. Hugs. Now remember, from our Arrhenius equation, we don't want K, we want the natural log of K. So those K values that I put into my calculator need to be the natural log of them. So once again, I can say, I know it was hard before, but can you possibly change everything in list 2 to the natural log of list 2, Calci? And Calci will say, oh yes, I can do that too. And sure enough, it can. Now look at these temperatures. Remember from our Arrhenius equation that we don't care one bit of dog spit about the temperatures. We want the inverse or the reciprocal of the temperatures. So, great and powerful Calci that I am unworthy of, please change all of list 1 to the reciprocal of list 1. In a mighty voice, Calci will do that. And sure enough, in a booming voice of glory, Calci will do that for us. So now that we have our reciprocals of temperature and our natural logs of K, we can put this into a graphical form. So to show this graphically, I hit second stat plot, and I'm going to turn on the stat plot, and I apparently have something crazy here because x-axis should be L1 because that's the reciprocal of our temperatures, and the y-axis should be list 2 because that's our K, that's the natural log of our list of our values there. So second quit, if I zoom 9, it'll show me my graph. Now all of that information is very useful with the exception of I need the slope in order to find the activation energy. So in order to find the slope, I am going to do stat, calculate a linear regression, and it's naturally going to do list 1 versus list 2, so I don't need to do anything there. I can, however, store it into y1 by doing my vars, y1 vars, and hit enter, and I'll end up with my y equals mx plus b. So the slope of this line is negative 1435.7. Now we know that the slope equals the activation energy divided by R. If we rewrite this formula to just get activation energy, it would be negative R times N equals the activation energy. So we're going to do this number times 8.0 8.31 will give us our activation energy. Once you do all the math, you find that activation energy equals 11,930. Let's put that as in kilos. So that would be 11.9 kilo. Kilo what, though? Well, we're talking about energy. And we know that 8.31 is joules per Kelvin mole. So what did we end up doing in our actual Arrhenius equation? We're multiplying by the reciprocal of temperature. So that means that our answer would have to have joules per Kelvin mole and joules per mole and no Kelvin, because we're multiplying by a temperature. So our units for activation energy are going to be kilojoules per mole. All right, next we're asked to find the value of K when temperature is 455 Kelvin. All right, so let's not lose track of what we have on our graph. On the x-axis, we have the reciprocal of our temperatures in Kelvin, and on the y-axis, we have the ln's, the natural log of our K values. So if we're given a temperature and we're asked to find K, we're looking for Y when X is 1 over 455, because remember, it's the reciprocal of our temperatures. So the reciprocal of 455 equals X. So we're going to do this like we did before, and we're going to say second calculate, and we have a value for X. We know that X is 455 to the minus 1. Hit enter and I'm going to be told, no, you can't do that. Okay, so let's figure out why we can't do that. It's probably because, ooh, went to the wrong place. It's probably because this window doesn't allow us to. So let's zoom out. So zoom out. Okay, now that we've zoomed out, we can probably calculate a value for X. 455 to the minus 1, and we find that Y at that value is 24.9. So we can't just say that that's our K value, because remember, Y is not just K, it's the natural log of K. So we need to get rid of the natural log by raising E to this value. So to do that, second quit, and we say second ln to get E to the, and we're going to raise it to whatever is stored in Y, because it stores it as that value. So we get 6.6 times 10 to the 10th, let's call it 66 times 10 to the 9th, so it's in line with our table above. All right, the last problem asks us to calculate the value, or calculate the temperature when the rate constant's given. Well, the rate constant is K. So again, remember that that's going to go on the y-axis, but not it exactly. It is the natural log of that value. And to do that, we simply say y equals, and we have a value for y, so let's go ahead and put that in. It is the natural log of 22.5 times 10, so I'm going to skip a step and do E, to the 9th. So we have that value. We say graph, and we're going to be given an intersect. Second calc 5 to do the intersect. This is our first line, this is our second line. Oh great, compy, please guess. And it says that the x at value, the value of x at that point, is 0.002, but remember, it's not just, that's not our temperature value, that's the reciprocal of our temperature value. So to get the actual temperature value, we can do x to the minus 1, because the reciprocal of the reciprocal is the original. So it's 339.1, so let's call it 339. And to double check, we can make sure that falls in line with our table. 339 would be between these two values. Is 22.5 between these two? And it is. So that looks like a good answer.